Doesn't matter if you want to replace your software developers, cheat on your university paper, or simply break into voice-authenticated government account. You can do all of it with modern AI technologies. But massive AI setups require quite a sophisticated data center with a network that will not become a bottleneck. Let's check how those networks are built. Hi, I'm Alex and it is NextGen channel. And today I have some real next-gen stuff for you. Let's make it work. So-called artificial intelligence is in fact the well-known neural network that must be processed layer by layer. Calculations of chunks of a next layer can be quite effectively paralleled between multiple GPUs. But to do those calculations, GPUs must have full view of the previous layer. So every time GPUs complete the execution of their portion of the model layer, every GPU must send results of the calculations to every other GPU, performing all-to-all reduction. Only then the execution can proceed to next model layer. And this data exchange between GPUs is the moment when a network could become a real bottleneck. A single query to LLM model with 70 billion parameters, with 8,000 input tokens and 256 output tokens, requires 20 gigabytes of synchronization data to be transferred from each GPU, as multiple queries could be processed in parallel through batching. To improve interference throughput, the amount of data transferred multiplies. So if you are trying to use general purpose services with still pretty standard 10 gigabit per second connections, it will take 16 seconds just to transfer data between GPUs and individual servers. And even this number is optimistic, as we have to add network latency, operating system network stack processing, TCP or UDP headers consuming bandwidth, and so on. So if you bought a server with a GPU, try to implement some models, like it, and want to add one more server to double performance, it's not gonna happen. For now, NVIDIA absolutely dominates the AI hardware field, so their design is a good starting point. But there is already a set of standards in preparation to replace proprietary NVIDIA solutions, and I will talk about those alternatives later. I'll start with the very cutting-edge solution and go to more down-to-earth variants that can be implemented for less than $1 zillion. To make inter-GPU data communication faster, NVIDIA developed an NVLink technology that allows GPUs to directly send data to each other. NVLink is not made of SLI. That used to combine multiple gaming GPUs into one logical, but shares the same idea. Each GPU has a set of communication lines that allows it to send and receive data from other GPUs. Both NVIDIA's Hopper and the latest Blackwell architecture have 18 communication lines per GPU. Hopper GPU can communicate 900 gigabytes per second of data through them, and Blackwell GPU can do twice as much, 1800 gigabytes per second. Numbers are absolutely stunning, but if you check closely, it's not out of this world. Let's check the Blackwell. 1800 gigabytes per second includes both transfer and receive, so it's actually 900 gigabytes per second one way. 900 gigabytes per second multiplied by 8 bits per byte gives us 7200 gigabits per second. Divided by 18 lines gives us 400 gigabits per line. Still a lot, but there is already 400 and even 800 gigabit Ethernet switches available. But there is a catch. Two GPUs in one system can have all the NVLinks connected to each other and can use all of its throughput. But if you have 4 or 8 GPUs, the number of links between each pair drops, and so does the speed. So NVIDIA developed one more solution, the NVLink switch chip. Yeah, that's how it's called, it's not just NV switch. Now, each GPU can just send data to switches, which will replicate it like a multicast packets and deliver it to other GPUs at full speed. NVLink Switch version 4 supports up to 8 GPUs with 900 GB per second between each pair. NVLink Switch version 5 is an absolute beast. It supports up to 576 GPUs with 1800 GB per second between each pair. Check this picture from NVIDIA. Those 4 at the server's motherboard bottom are NVLink switch chips. Main moment to be aware: NVLink is not InfiniBand or Ethernet. It's a custom solution. Its operations are all software-defined and controlled by NVIDIA SHARP, stands for Scalable Hierarchical Aggregation and Reduction Protocol, which controls not only data transfer but also resource allocation of the service CPU and GPU and how multiple jobs run in parallel. NVLink also supports GPU RDMA, Remote Direct Memory Access, that allows data to be written directly into GPU's memory without processing by CPU. And it reduces communication latency a lot. Okay, now you have a network between GPUs inside your server. But what if you need more than 8 GPUs, but still want the speed of NVLink? Well, then you need NVLink switch, but now it's an actual physical switch with NVLink switch chips in it. Now we're entering a little bit of gray area here, as you cannot just go and buy such a switch. As I know, it's only available as a part of complete systems, and even those systems have just become available, so everything below is my personal understanding of the data available for this moment, and I could be wrong. This photo is one of those physical NVLink 4 switches. It has 2 NVLink switch chips and 32 OSFP ports, each processing 4 NVLink lines. A fabric of those can theoretically connect up to 32 servers with 8 GPUs each. Transceivers used for them are standard OSFP transceivers with custom firmware to support NVLink. Quite an interesting transceiver, as it can have 2 separate external ports. That's how you get 800 gigabits links per port with 2 400 gigabits connections. NVLink 5 physical switch went even further, as it was made with NVL72 system in mind. This whole rack solution has 18 servers with 4 GPUs each, 72 GPUs in total, that's why it's called NVL72. It also has NVLink switches that are connected to servers using custom and, according to a guy in a leather jacket, very heavy copper cable system. They call it cartridge. And those switches can be connected to a spine level of NVLink switches, combining a set of 8 such racks into a single enormous GPU. 8 racks with 72 GPUs per rack will be 576 GPUs. And as you remember, it was the maximum number of GPUs supported by NVLink switch version 5. Not everyone is happy with NVIDIA making billions of dollars using their proprietary solution. So major players such as AMD, Alibaba, Apple, Cisco, Google, Intel, and so on, developing open standard to replace NVLink. They call it UltraEthernet Link, UALink. The closest analogy will be AMD's Infinity Fabric Link that connects AMD's chiplets in their processors. The main idea behind UALink, apart from pushing NVIDIA side, is to provide different component manufacturers with a unified way to communicate with other manufactured components. They call it accelerators. So you can have servers with GPUs from one vendor, servers with some kind of custom ASICs from other vendor, and everything will work extremely powerful unit. The first version of the standard has been published recently, but I haven't seen any product supporting it yet. Main parameters of this link will be 200 gigabits per line with option to combine lines. UALink switches are capable of connecting up to 1024 accelerators, and it supports encryption. Okay, what if it is way too expensive for your setup? Well, then good old PCI Express can still do the job. PCI Express version 5 X16 mode can transfer up to 128 gigabytes of data per second from each GPU, which is a lot, but almost 10 times slower than the latest NVLink. And if you have a lot of GPUs per server, you probably will not have enough PCI lines to provide 16 PCI Express lines for every GPU. Okay, but what if you need more? Like thousands and thousands of servers, or simply don't want to pay for proprietary stuff? Then the next option is Infiniband. Infiniband is a very mature technology, well known and widely used in high-performance computing for ages. As it was initially created with large computer system in mind, it has several major advances compared to classical Ethernet. The main one is RDMA, Remote Direct Memory Access. when data is written directly into chip memory instead of going through the CPU and operating system stack. As a result, less CPU requirements, much lower latency. Talking about the latest available models, Infiniband is still slower than NVLink. 800 gigabits per second per GPU against 900 gigabytes one way per second per GPU. But scalability make it a much more interesting and widely used solution in AI data centers. What's even more interesting, it's possible to have both NVLink between GPUs and Infiniband between servers. Infiniband topology is usually a fat tree topology, which is basically the same classical spine and leaf, but without oversubscription of uplinks. Or slightly insane dragonfly topology, where you connect groups of leaves to each other directly without spines. Each server can have an individual Infiniband network card for each installed GPU. Again, OSFP transceivers with dual fiber connectors provide up to 800 gigabits per second per port. One more thing. Yeah, Infiniband is an open standard and multiple companies make cards and switches, but let's keep it real. Saying Infiniband, we usually mean Mellanox as a manufacturer, and NVIDIA bought Mellanox. So we're getting back to the same manufacturer everywhere. But NVIDIA doing a really good job here. They implemented their SHARP protocol used in NVLink in their Infiniband solutions to significantly optimizing load. Their biggest classical Infiniband switch, Quantum X800, has 144 800 gigabits per second ports, allowing up to 10,000 GPUs fabric with spine and leaf topology. But they also have Quantum X photonic switch, which is an absolute technological marvel. It is also an Infiniband switch, but has photonic modules built directly into the communication chip inside the switch. So there are no transceivers, meaning no digital signal processor, meaning even lower latency. Switch ports are just passive fiber connectors, with light going directly into communication ASIC. Lasers for outgoing communication are put as separate modules, not directly connected to external cables. That block of modules on top of the switch are laser generators, not classical transceivers. Infiniband was a standard for high-performance computing for quite a while, but it has several issues. The main one is expensive. And second, it requires separate set of switches for Infiniband fabric and separate Ethernet switches for everything else. It would be much easier if we could get Infiniband features using an Ethernet network. So RDMA over converged Ethernet standard was made. It was not the only standard made for this task, but for now it's the most commonly accepted. Pretty simple idea. Use Infiniband transport level protocol on top of Ethernet frames. And in most commonly used these days RoCE v2 on top of IP UDP protocol. This way, by using special network cards with RoCE support, we can get RDMA communication using Ethernet switches. The problem is, it is normal for Ethernet network to have packet drops. It is actually designed with those drops in mind and has multiple mechanisms to detect and adjust its behavior depending on how many drops we have. It is a massive problem for RDMA, and the bigger your setup, the worse the situation. So several workarounds have been developed. Mainly, priority flow control, which allows switches to notify adjacent device that its packet buffer for priority queue is close to being full and data transfer should be delayed. Second, explicit congestion notification, in situation when congestion information needed to be propagated end-to-end. Implement those and you can call your network a converged Ethernet. At least PFC is absolutely necessary, but it requires hardware support, so not any Ethernet switch can be used. Worth mentioning that those solutions are workarounds that significantly reduce issues but do not eliminate them completely. Some packet drops still could happen, as a fabric-wide congestion avoidance is a form of high-skilled magic. The second problem is packet reordering during transition, partially mitigated by the fact that data exchange between a pair of nodes is a single UDP flow, so there can be no inflow load balancing. But still, something like a network interface card intelligent enough to reorder those packets could be needed. To eliminate the mentioned issues completely, UltraEthernet standard is in development by the UltraEthernet consortium. But the problem is UltraEthernet changes so many things compared to converged Ethernet. It will most probably require special ASICs, meaning new switches, meaning just buy InfiniBand. Now a billion-dollar question. What is better, InfiniBand or RoCE for an AI data center? Speed? Similar, 800 gigabits per second. RDMA? Both have. Latency? InfiniBand is slightly faster, but specific models of Ethernet switches, as per datasheet, have close latency. 100 nanoseconds InfiniBand against 230 nanoseconds Ethernet. But NVIDIA's Sharp-enabled InfiniBand networks claim to push latency even lower. Lossless communication. InfiniBand is still better. Configuration. InfiniBand is much simpler. Price. The total cost of all Ethernet solution is lower than InfiniBand. Provision time and overall availability. Ethernet is much better due to a wide range of manufacturers and models available. So, InfiniBand is better by a small margin, but costs more and could take more time to procure. It makes sense to use InfiniBand for massive setups, where small individual margins quickly became a big deal. For smaller setups, I'd recommend RoCE over InfiniBand. Requirements for storage in AI data centers are significantly lower comparing to inter-GPU connectivity. Both Ethernet and InfiniBand, if you have a lot of money, can be used. The main thing, storage traffic should not go through the same service interfaces as inter-GPU traffic. So servers should have separate storage NICs. Management and connectivity to non-AI service should go through a separate network too, but requirements here are so low, so pretty much any classical Ethernet network will be okay. All-in version of AI data center network. NVLink or UALink between GPUs within a server. Servers combined into pods using NVLink or UALink switches. Pods combined into superpods using spine NVLink or UALink switches. InfiniBand fabric for even bigger setups, with each server having a dedicated NIC for each GPU. Dedicated InfiniBand fabric for storage, dedicated Ethernet switches for management and connectivity to non-AI part of the data center. Balanced network version. NVLink between GPUs within a server, InfiniBand fabric for large-scale setups or RoCE for smaller-scale setups, dedicated high-throughput Ethernet fabric for storage, dedicated Ethernet switches for management and connectivity to non-AI part of the data center. Realistic network version. PCI Express between GPUs within a server, RoCE fabric between servers, dedicated Ethernet network for storage, remote access and connectivity to non-AI parts of the data center. In the garage startup version, there is only one network fabric with RDMA traffic prioritized using quality of service configuration. Depending on your specific scenario, solution could be between those mentioned. That's it for today. Thank you for watching. Share, like, subscribe. See you next time.